This is the first part of chapter on dienes, and in it we are going to examine nomenclature, isomerism, physical properties, and reactions of dienes. Any molecule with two carbon-carbon double bonds is a diene. Here we have three examples of dienes. So two double bonds may be part of an open chain compound, they may be part of a ring, or they may be part of a ring or a chain outside the ring. If there are three carbon-carbon double bonds in a compound, such compound is a triene. With 4 we have a tetraene, 5 pentaene, and so on. If there is a very large number of double bonds in a molecule, such molecule is called a polyene. Based on nature of double bonds in a molecule, we can classify dienes into three classes. In an isolated diene, double bonds are separated from each other by more than one single bond. In a conjugated diene, double bonds are separated from each other by one single bond. And finally, in a cumulated diene, double bonds are next to each other. So double bonds are on the same carbon atom. Note how we show that carbon atom in line formula. We show it with a dot, or we can use symbol C to do that. We cannot simply draw two double bonds that are connecting because we don't know how many carbon atoms are in between. So we have to show such carbon atoms of cumulated double bonds either as a dot or with symbol for carbon C. To name a diene, we should follow IUPAC nomenclature, and that means that we apply the following rules. First, we identify the longest chain that contains both of the double bonds. So even if there is a longer chain in the molecule but does not contain both of the double bonds, then the parent chain is one that contains both double bonds. We would ignore other chain. We should name that chain as an alkane and then replace the suffix ane of the alkane with suffix diene. Next, we should assign the two double bonds the lowest possible set of numbers. Then we should number and name the substituents. Finally, list the substituents in alphabetical order before the name of the parent chain. Here are some examples of nomenclature of dienes. This first example is straight chain of 5 carbon atoms. Therefore, parent chain is pentane. Because this is diene, we will replace a suffix ane with diene. So this is pentadiene. Double bonds are in positions 1 and 3, so this is 1,3-pentadiene. In this example, we have a 6-membered ring. Therefore, this is cyclohexane. Since there are two double bonds, this is cyclohexadiene. Two double bonds are in positions 1 and 4. You can number those yourself, starting with one of the double bonds. Of course, carbons of each double bond must be numbered consecutively, so it means 1, 2, and 4, 5. And you can number them clockwise or counterclockwise, and you will see that this is 1,4-cyclohexadiene. In the next example, we have 4 carbon chain, so butane. Since this is diene, this is butadiene, and double bonds are in positions 1 and 2. So this is 1,2-butadiene. This last example is a little bit more complex because it also contains a substituent, a methyl group. The longest chain that contains two double bonds is pentane chain. So we name it as pentadiene. Double bonds are in positions 1 and 3. So we have 1,3-pentadiene. Substituent is methyl group. It is on the second carbon, so complete name is 2-methyl-1,3-pentadiene. Here is another more complex compound. We should number diene in a ring in such a way that substituents get the smallest possible numbers. We could number these two double bonds from 1 to 4 either clockwise or counterclockwise. We will number it in such a way that methyl substituent gets the smaller possible number. That means it must have number 2. That leaves us with number 5 for, or position 5 for bromo substituent. So 6-membered ring, this is cyclohexadiene. Double bonds are in positions 1 and 3. So 1,3 cyclohexadiene. In position 2 we have methyl group, so 2-methyl, 1,3 cyclohexadiene, and finally in position 5 we have bromine. So 5-bromo, 2-methyl, 1,3 cyclohexadiene. And here is an example of a triene. Nomenclature is the same as in case of dienes, but since we have 3 double bonds, this is a triene. So suffix is triene. There are 6 carbons in the chain, in the parent chain, so this is hexatriene. And double bonds are in positions 1, 3, and 5. So name of this compound is 1,3,5-hexatriene. Now that you know how to name dienes, we can go on to more complex compounds, and those would be any substituted alkenes, not just dienes. To name any substituted alkene, you should follow this set of rules. First, identify the longest chain that contains both of the functional groups, alkene group and another functional group. Such chain would be the parent chain. Suffix should contain both functional group designations. "-ene" for double bond, suffix "-ene" for double bond is written first, and we usually omit the final "e". That's to avoid having too many vowels, well, 2 vowels next to each other. Then we should include the number corresponding to the first functional group, that's double bond, and we should include that number before the name of the parent chain. We should split the suffix and write the number corresponding to the second functional group before the suffix of that functional group. You will see that on an example. Finally, we should name and number substituents and list them in alphabetical order. And if it happens the chain contains both a double and a triple bond, then the chain is numbered so that it contains the lowest possible set of numbers. If there is a tie, then double bond gets the smaller number. So double bond has priority over a triple bond. Here are some examples. This is a straight chain compound. It has 7 carbons, so it would be heptane as an alkane. Because it has double bond and triple bond, it will have suffixes for those 2 functional groups. So "-ene" for double bond and "-ine" for triple bond. Therefore, this compound is an "-ene-ine". We number these 2 functional groups in such a way to give them smallest possible numbers. That means the triple bond will have number 1 and double bond number 5. We include number 5, which refers to double bond, before the name of the compound. So at the moment, name of the compound is 5-heptene-ine. And finally, we split the suffix. So we split "-ene" and "-ine, separate that with dashes, and in that separation include the number that refers to the second functional group, to "-ine", to triple bond. So that's number 1, which tells us the triple bond is between carbons 1 and 2. Therefore, complete name of this compound is 5-heptene-1-ine. Note also that we dropped the final "e" of "-ene". That's to avoid having "e" and "y" next to each other. Here is another more complex example. Note that parent chain is the longest chain that contains both functional groups. If you look carefully, you could actually find a longer chain, but that longer chain would contain only double bond. Therefore, this is not parent chain. Parent chain is one that contains both functional groups, and that's a chain of 6 carbon atoms. Therefore, hexane. Again, we have double and triple bond, so this is hexene-ine. We assign double and triple bond the smallest possible numbers, and that means the triple bond should get number 1 and double bond number 4. Following rules you just learned, we will include number for double bond before the name of the parent chain, so that's 4-hexene, and split the suffix, and in that split include number for the triple bond. That's number 1. So 4-hexene 1-ine. Finally, we should name the substituent. That's propyl group, and it's on carbon 3. So complete name is 3-propyl 4-hexene 1-ine. This final example looks very much like the first one. Difference is that now we have a tie. If we number the chain from left to right or right to left, either way we end up with same set of numbers, 2 and 5 for double and triple bond. So now we have a tie. To break a tie, we assign smaller number to double bond. So double bond has priority. That leaves number 5 larger number for triple bond. Therefore, correct name of this compound is 2-heptene 5-ine. If there is another functional group in a molecule that has priority higher than the alkene, then the chain is numbered so that the higher priority functional group gets the lowest possible number. At present, pretty much the only such functional group that you are aware of is the alcohol functional group, hydroxyl group. So we number the chain so that hydroxyl group gets the smallest possible number. We ignore the double bond and simply assign the smallest possible number to the OH group. There are other functional groups that have higher priority than the double or triple bond. Those would be various carbonyl groups, such as aldehydes, ketones, carboxylic acids, and amides. We will be covering those compounds as a part of Organic 2 course. So at the moment, you really need to worry about alcohols. In this first example, we have a 5-carbon parent chain, so it would be pentane. Because this is an alcohol and an alkene, the suffix is enol. So the compound is pentenol. We assign the smallest possible number to the OH group, and that's the number 1. And of course that leaves us with number 3 for double bond. Double bond is between carbons 3 and 4. As usual, number assigned to double bond is written before the name of the parent chain. So 3-pentene. We split the suffix into in and ol, and we insert number that denotes where OH group is, so 1-ol. That means complete name of this compound is 3-pentene 1-ol. Next compound is cyclic compound. In this compound, we will assign number 1 to carbon that carries OH group, and we name this compound as cyclohexenol. As in case of naming of cyclohexanol, we do not include number 1. So we understood or assumed that number 1 is the carbon that carries OH group, and that number is not listed. That means that now we don't have to split the suffix. If carbon with OH group is carbon 1, then double bond is between carbons 2 and 3, and methyl group is on the carbon 4. Therefore, overall name of the compound is 4-methyl 2-cyclohexenol. Again, we do not include number 1. It would be a mistake to name this compound as 4-methyl 2-cyclohexene 1-ol. Dienes are compounds with double bonds, and if carbons of the double bond have different substituents, then we have possibility for isomerism. This is cis-trans or EZ isomerism. In case of dienes, we always use EZ designation. Just to remind you, E stands for entgegen, and that means opposite. In other words, higher priority substituents are on opposite sides of the double bond. Z stands for zusammen or together. That means that higher priority substituents are on the same side of double bond. In addition, in case of dienes or compounds with more than one double bond, we have to include the number that precedes symbol E or Z. That number indicates which double bond symbol E or Z refers to. Each double bond can have two possible isomers, E or Z. And in compound with more than one double bond, we have all the possible isomers. So each double bond could be E or Z, and with 2 double bonds we have a maximum of 4 possible isomers. This is illustrated here on example of 2,4-heptadiene. We have 2E4E isomer, 2Z4E isomer, 2E4Z isomer, and finally 2Z4Z isomer. All those 4 are different isomers, and we have a maximum number of possible isomers. Note in particular that 2Z4E is different from 2E4Z. Sometimes number of isomers is fewer than the maximum possible number of isomers. In case of diene, maximum number of isomers is 4. Clearly, in case of 2,4-hexadiene, 2E4E and 2Z4Z isomers are different. But note that 2E4Z is identical to 2Z4E. That's because the molecule is symmetrical. So in this case, we have only 3 different isomers, and the last isomer can be named as either 2E4Z or 2Z4E. That doesn't really make any difference. Sometimes only one of the 2 double bonds of diene exhibits isomerism. That is the case if one of the carbons of the double bond has identical set of substituents. Then that double bond cannot exhibit isomerism. Only the other double bond, where each of the carbon atoms has different set of substituents, exhibits isomerism. Then we only need to indicate stereochemistry of that double bond. Since only one double bond exhibits isomerism, we don't need to use any numbers. It is clear that symbol E or Z refers only to that one double bond. So, for example, when it comes to naming isomeric 2-methyl-2,4-hexadienes, we can name them as either E 2-methyl-2,4-hexadiene or Z 2-methyl-2,4-hexadiene, depending on which isomer we want to name. Stabilities of dienes can be compared by comparing their heats of hydrogenation. In the course of a hydrogenation reaction, double bond is hydrogenated into a single bond. So a molecule of hydrogen is added across a pi bond in presence of a noble metal catalyst such as platinum. To compare heats of hydrogenations of various dienes, we compare dienes that give identical product. In this case, each of the 3 dienes gives identical product, pentane. That way we can compare their relative stabilities. Unstable dienes have high energy content and upon hydrogenation release large amount of energy. Stable dienes and in general stable compounds have low energy content and upon hydrogenation release less energy. So this is a convenient practical method to compare stabilities of different compounds. Hydrogenation of an alene, and that's 2,3-pentadiene, releases rather large amount of energy, 70.5 kilocalories per mole. So highly exothermic reaction. That means that in general alenes are not very stable. Compared to an alene, an isolated diene, 1,4-pentadiene, releases considerably less energy, 60.2 kilocalories per mole. This is expected amount. This is approximately the amount of energy that is released by each double bond. So 2 double bonds behave as if the other double bond is not present. So each double bond releases expected amount of energy, about 30 kilocalories per mole. Finally, conjugated diene, 1,3-pentadiene, releases the lowest amount of energy. It releases somewhat less than expected. So it releases 54.1 kilocalories per mole. This is less than what you would expect for 2 double bonds. That means that this is more stable compared to an isolated diene. In conclusion, overall stability of dienes increases in the order of cumulated, isolated, conjugated. We can consider isolated dienes to be default dienes. 2 double bonds behave as individual double bonds and they behave as if the other double bond was not present. Cumulated double bonds are considerably less stable than isolated double bonds, so there is considerable increase in energy, while conjugated dienes are more stable. We can relate stability of each diene to its hybridization. In a conjugated diene, all carbons are sp2 hybridized. So you can see that each carbon of the diene system is sp2 hybridized. Next, we can see an isolated diene, 1,4-pentadiene. Carbons of the double bond, as expected, are sp2 hybridized, but there is in the middle an sp3 hybridized carbon. Finally, in an alene, that means diene system that is an alene, terminal carbons, carbons at the end of diene system, are sp2 hybridized as expected. Middle carbon is sp hybridized. So note that middle carbon is sp hybridized. It makes two sp hybrid orbitals, and two unhybridized p orbitals are used to make each of the double bonds. Increased stability of conjugated diene can be explained by electron delocalization. Since we have all sp2 hybridized carbons, there is possibility for electron delocalization, which is shown as electron movement here by arrows. So double bonds actually overlap and delocalize over the entire diene system. This is shown in form of single formula underneath these resonance structures. So that means that there is really one diene system, one electron cloud that spreads over the entire diene system, and that, of course, lowers the energy of the system. So, in conclusion, conjugated dienes are more stable compared to isolated dienes because of the electron delocalization. In an alene, we have two double bonds that are very close to each other. And actually, if you look at structure of alene, it does resemble triple bond. And in fact, alenes in terms of energy are very close to alkynes. So in terms of energy and properties, alenes to an extent resemble alkynes. And you can see that at the bottom of the slide from heats of hydrogenation. Hydrogenation of an alene releases 70.5 kilocalories per mole. Hydrogenation of an equivalent alkyne compound with same number of carbon atoms releases 69.9 kilocalories per mole. Those are very similar numbers, and that shows us that alenes in properties are very similar to alkynes, and alkynes are less stable than alkenes. So to an extent that explains low stability of alenes. They have stability of alkynes. Finally, isolated alkanes or dienes have no increased or decreased stability. They have what you would consider default stability. That means stability that is expected from compound with two isolated double bonds. Because there is an sp3 hybridized carbon between the two double bonds, electron delocalization, and therefore such stabilization is not possible. This is molecular orbital explanation of electron delocalization. So molecular orbitals of 1,3-butadiene. On the left, we have ordinary alkene ethene. So we have pi bonds, bonding pi bond, and anti-bonding pi star orbital. You can see there is a large energy gap between them. In case of 1,3-butadiene, 4 individual atomic p orbitals overlap to make 4 molecular pi orbitals. And you should note that pi 1 orbital, one that is lowest in energy, envelops the entire system. So that shows electron delocalization. Pi 2 orbital is the way we usually represent 1,3-butadiene, so 2 individual double bonds. Pi 3 and pi 4 orbitals are antibonding, and they are empty under ordinary conditions. When we compare molecular orbitals of 1,3-butadiene with molecular orbitals of 1,4-pentadiene, we can see that the situation is very different. In 1,4-pentadiene, we have simply individual molecular pi orbitals, and they are identical to molecular orbitals of ethene. So each double bond is on its own. It has one bonding pi orbital and one antibonding pi star orbital. Unlike 1,3-butadiene, there is no that low-lying pi1 orbital that would envelop entire molecule. And that's why this one has lower stability, and this is stability, as I mentioned earlier, that we consider to be default stability of a diene. When it comes to reactions of dienes, isolated dienes react as expected. Each double bond reacts individually. It reacts as if the other double bond were not present. So as long as we use excess reagent, addition reactions proceed as expected. So in case of 1,4-pentadiene, reaction with excess hydrogen bromide proceeds according to Markovnikov rule. Each double bond undergoes addition of hydrogen bromide. Hydrogen adds to the carbon that contains more hydrogens. Bromine adds to the other carbon. And product is 2,4-dibromopentane. Underneath you can see the mechanism. So first one molecule of hydrogen bromide adds. The mechanism is usual via the carbocation intermediate, and after the first addition is completed, the other molecule adds following the same mechanism. So nothing new here, nothing unexpected. Simply the mechanism you learned earlier when we studied alkenes repeats here. If two double bonds are different, then their reactivity is different. One is more reactive than the other, and more reactive double bond will react preferentially. So if we use limited amount of reagent, only one double bond may react and the other may be left intact. Double bond that react is the more substituted double bond, because the more substituted double bond gives the more stable carbocation. In this case, we have two double bonds. Double bond on the left, double bond 1, has two substituents, methyl group and the rest of the molecule. On the other hand, double bond on the right, double bond 5, has only one substituent, which we would consider rest of the molecule. Addition of hydrogen from HCl to double bond on the left would give tertiary carbocation, while addition of hydrogen to double bond on the right would give secondary carbocation. Tertiary carbocation is more stable than secondary. That means that addition to double bond on the left is preferential and is really the only one that occurs under ordinary conditions. So we get only one product if we use one equivalent of HCl, and that is a 5-chloro derivative. So this compound is 5-chloro, 5-methyl, 1-hexene, the only product. Situation is far more complex if we consider reactions of conjugated dienes. Conjugated dienes act as a system, so entire diene system acts together. So two double bonds react together. You know that mechanism of reaction involves formation of carbocation. Well, carbocation is allylic carbocation and it's stabilized through resonance as shown here. So after addition of first hydrogen, we have carbocation and then we have two resonance structures. Either of the two resonance structures can react with nucleophile to give the product. So there are two possible products of the reaction. If we examine simplest addition of hydrogen bromide, or in this case hydrobromic acid, to 1,3-butadiene, first hydrogen adds to give the intermediate carbocation. Note that carbocation on the left is more substituted. It's secondary carbocation, and one on the right is primary, less substituted. So one on the left is more stable compared to one on the right. That one is going to form faster, and it will give us, of course, kinetic product. Kinetic product is one that forms faster in a reaction. So reaction of bromide anion with secondary carbocation gives kinetic product. This is what we call 1,2 addition, because hydrogen and bromine add to carbons 1 and 2 of the diene system. On the other hand, if bromine adds to the other carbocation, primary carbocation, we end up with so-called 1,4 addition, because hydrogen and bromine ended up on carbons 1 and 4 of diene system. Note, when we consider the products, that now double bonds are very different. In case of 1,2 addition, we end up with mono substituted double bond, while in case of 1,4 addition we ended up with di-substituted double bond. More substituted double bond is more stable double bond. That means that result of 1,4 addition is more stable compared to result or product of 1,2 addition. Therefore, 1,4 addition gives thermodynamic product, more stable product. So this reaction could give us two possible products. Kinetic product, one that forms faster, and that's 1,2 addition product. Or more stable product, that's thermodynamic product, and that's 1,4 addition product. Results of experiments confirm that if we do reaction at low temperature for a short time, we get preferentially kinetic product. If we do this reaction at minus 80 degrees Celsius, we get 80% of 1,2 addition product, kinetic product, and only 20% of 1,4 addition product or thermodynamic product. At 0 degrees, results are similar. This reaction was done in dichloromethane, and at 40 degrees boiling point of dichloromethane, that means the highest possible temperature at which we could do the reaction, the results are reversed. So at 40 degrees Celsius, we get only 15% of 1,2 addition of kinetic product and 85% of 1,4 reaction product or thermodynamic product. So we can control reaction conditions to get kinetic or thermodynamic product. Low reaction temperature and short reaction times are going to give us kinetic product. On the other hand, high reaction temperature and extended reaction times are going to result in formation of large amount or predominant amount of thermodynamic product. Here is how we explain kinetic and thermodynamic control of the reaction. If we consider reaction diagram, A is the starting material. It reacts to give the intermediate. In our case, intermediate is carbocation. On the right, species A, intermediate B and C are shown. So intermediate is carbocation stabilized through resonance, and that carbocation can give us two possible products. Product B, result of 1,2 addition. You can see activation energy to form product B is lower, so that's faster reaction. On the other hand, while activation energy to form product C, result of 1,4 addition, is higher, that's more stable product, so that's thermodynamic reaction. Therefore, depending on reaction conditions, we will get either product B or C preferentially. If reaction in general, in which starting material A gives mixture of B plus C, is not reversible, then those are kinetic. We always get kinetic product. Those are kinetic conditions. On the other hand, if at least one step of the reaction is reversible, either reaction of A to B or A to C or both, then reaction proceeds under thermodynamic control. Keep in mind that previous analysis applied to 1,3-butadiene. If we have different diene, then we have to repeat the analysis. So in this case of 2,4-hexadiene, we have products of 1,2 and 1,4 addition that are obviously very different. You can name them and you will see that they end up with different names. But these two carbocations are equally stable. They are both secondary allylic carbocations. And the two products, results of 1,2 and 1,4 addition, are equally stable. In each case, we have a di-substituted double bond. So in this case, regardless of reaction conditions, we would expect to get two reaction products in equal amount. That means that for each particular reaction, you should do analysis, consider stability of carbocations and stability of products. Product that is obtained via more stable carbocation is always kinetic product. Product that gives more stable double bond is always a thermodynamic product. Here is what we have covered today. Nomenclature of dienes, isomerism in dienes, physical properties of dienes, and reactions of isolated and conjugated dienes. Next day, we are going to examine one very important reaction of conjugated dienes, and that's Diels-Alder reaction.